Hello everyone. So, in the previous video, we had seen about the exponentially weighted averages. Okay. So, in this particular video, we'll be seeing the next topic, that is nothing but the gradient descent with momentum. The gradient descent with momentum. So, here the basic idea of the gradient descent is to calculate the exponentially weighted average of the gradient. Okay. So, consider this uh, you can see this is a red dot over here. Okay, so you have to optimize the cost function. Okay, so let's say that you would like to try to optimize the cost function which has a contour like this. So this is a contour like this. So so this red dot which is over here. Okay, so this is a contour. So the red dot is nothing but the, you can see the minimum. Okay, cost, or you can see this nothing but the minimum. Okay, is a position of the minimum. You can see the position of the minimum. So when I when and so initially you start the gradient descent somewhat here. So I need to reach this minimum point. Okay, so if you take one iteration of the gradient descent, so first step, because you are not aware of the global minimum, so you actually can take one step. Okay, and when you take one step, you will be reaching here. Okay, then you will be taking the second step. Okay, like this. Okay. Let me redraw this once again. So consider this the first step. Okay, so this is my first step. So initially my first step is over here. Okay, then I'll come to the second step, which is and the downward direction. Then again I come here third. This is again. So I'm trying to reach the minimum value. Okay, but so here you can see that okay, let me redraw this. Okay, so here you can see this is this one. So I have started from here, then I have reached this particular part. Okay, then I'm just seeing that, okay, whether I'm trying to am I in the right path or not. So again I'm going up. Okay, then I'm reaching again this particular part. Okay, which is, you can see that I'm coming near to the global minimum. Again I'm going up. Again I'm reaching downwards. Again I'm going up. Again I'm reaching here. Okay, again I'm going up. Again I'm reaching it. So like that, towards the end you can see that the oscillation flattens out little bit. Okay, so these what you can see the here, we can have a, you can see that there is a up and down oscillation in the beginning, and that is a major up and down oscillation which you can see here. Okay, and and in the toward the end, which you can see here, towards the end, okay, it slows down. Okay, and you get the gradient descent. Okay, so this prevents you from using much larger learning rate. Okay, so these up and down. Okay, uh, um, which you can say that it prevents you from using much larger, because at least you will have a direction. Okay, as to reach the uh, position of the minimum. Okay, if much larger learning rate is used, you might overshoot. So overshooting will take place. That is, you can see that it might go too much height. Okay, then or else then it might go, okay, too much low also. So this is actually the not the correct way, because too much overshooting, too much diversion diverging. So that is nothing, too much oscillation will take place. Hence, you might require a larger learning rate. Larger learning rate is required. Okay, larger learning rate is required. So too much of learning rate also um, will lead to reaching to the minimum. That is the time taken to reach the minimum is much larger. So it is better to have a smaller learning rate, which you can say this is a much smaller learning rate, as you can see here. Okay, much smaller learning rate. Okay. Okay. Another way of looking at this thing is, okay, on the vertical axis, you can see that this is the vertical thing. Okay, this is on the vertical, and this is nothing but the, sorry, this is the vertical, and this is the horizontal thing. So on the vertical, okay, things are a bit slower. Okay, so the learning rate is slower, whereas in the horizontal thing, this is my horizontal. Okay, the learning rate is faster. Okay, you see that initially when the oscillation was too much, so it was a vertical and it was a bit slower. As and when it became, it turned from vertical to horizontal, the learning rate became much faster. Okay, so this is the observation which you should know. So you can see that the horizontal learning rate will aggressively move towards the this red dot, that is the minimum. So on each iteration, okay, what you need to do is you need to have a change in the weights as well as the change in the error rate. So what is that? We compute the derivative of dw and db on the current mini batch, or you can say that mini batch gradient descent. So this is nothing but VDW is nothing but equal to beta VDW plus 1 minus beta VDW. So if you can observe this, okay, this is similar to we had seen in the previous video. Okay, that is VT is nothing but equal to beta VT plus 1 minus beta theta t, okay, which is we had seen in the previous case. Now, uh, just like the change in the weight, we also have to find out the weight for changing the biases. So VDB is nothing by beta VDB plus 1 minus beta VDB. Okay, then you would see that how the update your weight, okay, it takes place. Okay, so you would update your weight after this too. Okay, you would update your weight. So for updating your weights and the biases, okay, by using W is nothing but W minus alpha VDW and beta is nothing but equal to beta minus alpha, okay, VDB. Okay, so um, with the appropriate beta value, which we are taking, okay, we are using the we are ensuring that, okay, we are smoothing out the, okay, the weights and biases to reach out the minimum point. So to reach out the minimum, that is nothing but the red dot which you can see is that. So as you can see that if we are using the horizontal way, uh, okay, so it becomes much faster. Okay, so and if you're taking this as the vertical, it becomes, it takes more slower. So and alpha is nothing but the learning rate which we are taking. So as you see that if there is not much distortion, you can say, if there is not much variation, or oscillation, then there will be a better learning rate. Okay, and if we are having the learning the movement of the weights, or let's say the movement of this uh, nodes of that is weights is toward the horizontal axis, or you can say for um, if you're taking the horizontal path, then the uh, the chances of reaching to the global minimum is higher. So that is something. If the horizontal, if we are taking the horizontal direction, so the gradient descent will be moving much quickly this way than if you are taking the vertical direction. So if you are taking in this way, so it will be much faster. So this will take algorithm to take its much straightforward path to damp out the oscillation. This is similar to, just like we can see that if we are taking an example, okay, like you are having a bowl over here, okay, a bowl, okay. So I'm just relating to this to physics, where you can see that this is a bowl and you are throwing a ball in this, okay. So it has to move in this particular direction. So it will move till it reaches the minimum. So the consider this equation VdW is equal to beta VdW plus 1 minus beta dW. So here beta, which is what I said, okay, is the amount of movement what is required for the weights to be moved. That is for smoothing out the weight. Whether you want the weight to be more smooth, or you can if you want it to be much much more distorted or something like that, which we have seen. So, or with higher beta value, you will have a smoother value. So this will decide on the friction. Okay, that is there. Okay, when the ball is moving towards down, VdW we can say it is like a velocity. Okay, at which the ball is moving downwards, and dW is nothing but this dW. Okay, is nothing but the acceleration. It is nothing but an acceleration. That is the at speed it is going downwards. Okay, the speed at which it is going down. So this VdW, not dW, this VdW is acting like a acceleration. This VdW, that is beta VdW, is acting like a the velocity, and this particular thing is acting like an acceleration. So this is the same thing, like how the ball is reaching to the minimum. So you can see that if it is taken the more uh, horizontal path, so you will be reaching the minimum point as quickly as possible. Okay, so that is about the gradient descent. Okay, with momentum. So this why I have taken this physics example, because you can relate this to physics that as we are taking the more horizontal path, okay, over here, it will take much more easier. It will be much more easier to read. If we are not taking that path, this consider we are taking the horizontal path. Consider if we are taking in this way. Okay, so it will take much more time to reach the minimum. So you see the amount of you can say that uh, the to reach the minimum. Okay, it has to come here, then from here to here, then here to here, then here to here. So you can see that it has to. There is much more distortion. Okay, that will be taking place over here. Okay, so so this actually will have a more you can say the amount of average, you can say this is more, which we had discussed in the previous video. So the average between the weights will also be more in this case, where in this case the average between the weights is less. Okay, and although the you can say it will have some um, more results, but at least it will reach the global minimum as quickly as possible than from than taking the horizontal path. Okay, yeah. So thank you.